Hello and welcome to week 7 of the live problem solving session for the course Introduction to Semiconductor Devices by Professor Naresh Kumar Imani from IIT Hyderabad. The course ID is NOC 25E92. I am Mayank Goyal. I am a research scholar at the Department of Electrical Engineering, IIT Bombay. The course is being taught by Professor Naresh Kumar Imani, who is an associate professor at the Department of Electrical Engineering, IIT Hyderabad. The plan for this week is MOS capacitors, their analysis of field effect, electric field potential diagrams, energy band diagrams, accumulation and inversion regimes, gate voltage drop across a MOS device. This session is being held every Sunday 6 p.m. to 8 p.m. at this Google Meet link. So first we will do a recap of the lecture. So we start with energy band diagrams of MOS capacitor. So last week we had studied a MOS capacitor means metal oxide semiconductor. So you have a metal and a semiconductor, and there's an oxide in between, which acts as an insulator. And so the metal side and the semiconductor side act as the act as the plates of a parallel plate capacitor. So now how to draw an energy band diagram for this? So so you have three components: one metal, one oxide, one semiconductor. First, you have to draw individual band diagrams for each of them. So for metal, the only band diagram would be the Fermi level, which is the only band diagram for metal is the Fermi level, which will be. So first you have to draw a vacuum level. So the vacuum level will be common for all of them. It's a straight line. It will be common for all of them when they are not connected. So for metal, the band diagram would be the Fermi level, which is at a distance of the work function of the metal. So this is phi m, which is the work function of the metal. E phi m is the metal Fermi level. Then for oxide, we take the electron affinity for the oxide and the band gap. So we don't draw the mid gap or the Fermi level for the oxide because that is not known because it's an insulator. So it's very hard to determine the Fermi level for the oxide. So you only draw the conduction band and the valence band, and the gaps we use is the electron affinity of the oxide and the band gap of the oxide. For the semiconductor, we have the electron conduction band, the valence band, the mid gap, and the Fermi level. So Fermi level is determined by the doping. So you have the band, you have the electron affinity of the semiconductor, which in case of silicon will be around 4 eV. So for oxide, for silicon dioxide, your f- ba- electron affinity is around 0.95 eV and your band gap is around 9 eV. For silicon, the electron affinity is around 4 eV. The band gap is around 1.1 eV, and the Fermi level position is determined by the doping, and the distance between mid gap and the Fermi level is called phi f, which is your Fermi energy, Fermi potential. And the and this and if you take the Fermi level from the if you take the distance of Fermi level from the vacuum level, it is called phi s, which is your this thing. Phi s is your work function of the semiconductor. So phi s can be calculated by adding up your E psi with E chi, which is your electron affinity, plus Eg by 2, plus your phi f, which is your Fermi potential. Or in the case, this is in the case of P type, the Fermi potential is below the mid gap, so it's plus phi f. For N type material, the Fermi level will be above the mid gap, so it will be minus phi f. So chi plus Eg by 2 minus phi f for N type, chi plus Eg by 2 plus phi f for P type. That's how you will get the where phi s, which is work function of the semiconductor, and your phi m, which is the work function of the metal. So to get the difference between the two, which is phi ms, you do phi ms is equal to phi m minus phi s. And if we consider ideal MOS capacitors, your phi ms will be 0. So your phi m and phi s will be at the same value for in ideal case. So this is how it will look for ideal case. So if your phi ms is 0, there will be no band bending, and it will all be straight lines. So your metal, that means your metal work function and your semiconductor work function is the same level. So the Fermi level will be at the same distance on the vacuum level. So you draw the Fermi level come together. Then according to the Fermi level, you draw your EC, EI, and EV. And the vacuum level, from the vacuum level, you can draw your oxide EC and EV. And if you don't want to consider the Fermi level, you can just we know it's a we know the electron affinity for semiconductor silicon is 4 eV, and the electron affinity of silicon dioxide is 0.95 eV. So if we subtract that, we will get 3.05 eV. So we will know the difference between the EC of the two is 3.05 eV, and the band gap is 9 eV. So you can use just that values to draw your oxide. Now, there, when you apply bias, it can go. Last week we studied when you apply bias, it can go into accumulation, depletion, or inversion. So first is accumulation. In accumulation, your electric field is from semiconductor to the metal for for a p-type semiconductor. This is for a p-type semiconductor, which is, so we had studied last week that a p-type semiconductor is called an NMOS, and an n-type semiconductor is called a PMOS capacitor. So for a NMOS capacitor where the semiconductor is p-type, we apply negative voltage. Your metal band shifts upwards, and because of that, your Fermi level at the semiconductor also shifts upwards. So there is an overall net upwards band bending. Due to this upwards band bending, there's a addition of your Fermi level becomes closer to your band. Your Fermi level becomes closer to your work function. Fermi level becomes closer to your valence band, which means there are more p-type charges here compared. There was already, so that means, so it's a p-type semiconductor. So holes were already majority carriers. Now there are even more holes. So that is called that. That means that holes are getting accumulated in this region. That is why it's called accumulation. And the and on the oxide also you will see there's a band bending. So the oxide band bending is given by the direction of the electric field. So if the electric field is in the negative direction, then the oxide band bending will be like this, will have negative slope. And if the electric field is in the positive direction, then oxide will have a positive slope. Oxide bands. Now if we calculate the capacitance, so if we calculate the capacitance of this, then capacitance will be Cox. The capacitance will only consider, we will only consider the oxide capacitance. So that's Cox, which is equal to epsilon Ox by Tox. So epsilon Ox is the dielectric constant of the oxide, and Tox is the thickness of the oxide here. So if we draw the charge accumulation accordingly, so you will see there will be a negative charge accumulate, since it is at negative bias, there will be a accumulation of negative charge here, and there's a accumulation of holes at the surface here. So there will be a net positive charge on the semiconductor side, but their thicknesses will be almost negligible because they are only at the this charge accumulation is only at the interface with the oxide. So the negligible thickness, negative and positive. And if if you want to draw the electric field, so you electric field is given by the integration of the integration of charges. So there is no charges in the negative region, so the electric field is negative. As but here at the interface it experiences a high negative charge, so it becomes negative. So you can, and at the semiconductor oxide interface it encounters a high positive charge, so electric field again becomes from negative to zero, and then it's zero continuously. So you can see only in the oxide region we have electric field, and that is at a negative value. Hence, hence the oxide band has a negative slope. Now when now from electric field you can calculate potential. So potential again it will be, if it's an integration of electric field, so it's zero, then it encounters a potential value. So it start so it's a constant. When you integrate a constant you will get a straight line, so it's a straight line. And then it becomes zero. then it then it's zero, so it's constant again. So potential is negative of integration, so it becomes like this. So you can see there's a, in the bulk region the potential is zero, but in the oxide there's a potential gap which is equal to your Vg that you have applied. Then this depletion region. So when you apply a positive voltage at the metal interface, at the metal shifts down. So it also shifts the bands of the p-type semiconductor down. And hence the Fermi level moves away from the valence band. So that means the holes in this region are getting depleted. Hence it's called depletion region. So there's now a depletion region formed in this region. So now if you draw the charges in this case, then so for metal again you will have, since you have applied a positive charge, you have a positive charge here, but it's only at the interface since it's a metal. So in the bulk there will be no charge accumulation in the metal, so only at the interface there can be charge accumulation. So in the metal the plus charge is at the interface only, while in the semiconductor you have a depletion regions, a large space charge region with a width of W, and it, since there's a depletion of holes, so it's negatively charged. So now when you integrate it for to get electric field, again you have zero charge here, then you suddenly encounter a positive charge, so you get a positive charge value here. Then you are encountering a negative charge region. So when you integrate it, you will get slowly go back to zero as in a straight line. So your electric field will look like this. Then when you integrate the, so you can now calculate this straight line, which will come out to be q na by epsilon si w minus x. This you can solve from this from your charges. You can solve. Then oxide, here you can see the oxide. Oxide oxide is in the positive region. The electric field is positive in the oxide. So hence the oxide band bending will have positive slope. So you can see now you will have a, so you have a zero, then you have a constant positive value which then starts decreasing till zero. And now one thing will be that the electric field in the oxide will not be same as the electric field in the semiconductor, because they have a different different dielectric constants. So the electric field in the oxide will be equal to epsilon Si by epsilon ox, electric field in the silicon. So epsilon Si is given as 11.7, epsilon SiO2 is 3.9. So this is around 3 times. So the electric field in the oxide will be around 3 times the value of the electric field at the semiconductor in the semiconductor interface. So semiconductor electric field we have calculated as Q Na by epsilon Si into W. So the electric field in the oxide will be 3 times of that value. Now when you now for calculating potential you have to integrate it and then make it negative. so so when you do that you will have a exponentially rising value here, not exponentially, it will be square. So it's linear, so it's linear value here, so it's a ex, integration will be square. So you have a square rise here, and then this is constant, so you have a constant here, and you will see there's a band, there's a potential shift here which is equal to your applied potential Vg. And you can also calculate the value at the value for this is will come out to be Q Na by 2 epsilon Si W minus X whole square. So now you can split this into two regions. One is oxide region and one is semiconductor region. So the net rise is equal to Vg, but some portion of it is in oxide which is called Vox, and some portion of it is in the semiconductor which is called psi s. So psi s is called a surface potential, which is your change in the change in potential in the semiconductor region. So your net is Vg equals to Vox plus psi s, where Vox is the potential drop in the oxide and psi s is in the potential drop in the semiconductor. So another way to look at psi s is the band bending. So how much the band has bent, that can also give you your psi s. So you can calculate as psi s equals to Ei bulk minus Ei surface, which is how what was the your Ei in the bulk and what is your Ei at the surface. So when there is no band bending, that is the flat band region where band bending is not there. So your Ei bulk and Ei surface are same. So your psi s is 0 in the flat band condition. So by this you can also calculate your psi s at the threshold. So the point where your so if the threshold is the point when your EF and EI meet at the interface. So in that case, your EI bulk minus EI surface will if we take EF as reference for calculating EI, then for at bulk it's equal to phi F and at surface it's equal to 0 because they are merging. So we calculate psi s is equal to phi F minus 0 equals to phi F. So at the threshold, that is when both of them are touching each other, that at that time your psi s is equal to phi F. And in the inversion region, so at the maximum inversion point, your it's your at the band. So condition at the interface is the opposite of the condition at the bulk. That means at in the bulk, if your Fermi level was 5f below the Fermi level was 5f below the mid gap, below EI. At the interface, Fermi level is 5f above your EI. So at this point, if you calculate, your psi s will be 5f minus, here it will be minus 5f because now it's in the opposite direction. So it will be 2 5f. So in the inversion region, your at maximum band bending, your 5s is equal to 2 5f. So you see, so you have flat band. In the left of the flat band you have accumulation. Right of the flat band you have depletion till threshold. After threshold it's inversion till so now you can calculate your relationship between Vg and psi s, sorry. Vg is Vox plus psi s. We have seen that Vox you can calculate as epsilon ox Tox and epsilon sorry, Eox into Tox. This is electric field. Eox into Tox. Eox we know is epsilon Si by epsilon ox into ESI, and ESI we know is QNA by epsilon Si into W. So you put all of this into this, you will get it as minus QNAW by epsilon ox by Tox plus psi s. So QNAW is your QD, your depletion charge. Depletion charge we know is QNAW. Epsilon ox by Tox is Cox, that we know. So here Vg comes out to be Vg equals to minus Qd by Cox plus epsilon s, sorry, plus psi s. So from here, so till now we were studying NMOS devices where your semiconductor is p-type. Now for a PMOS device where semiconductor is n-type, for accumulation you have to give your positive 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 value at the metal. Your band will move downwards, making it more Fermi level is becoming more closer to conduction band, hence accumulation of electrons. This is how your charge distribution will look. A very thin layer at the interface, plus q at the for plus q charges for because positive positive voltage given at metal, and minus q charges due to electron accumulation. For depletion region you give negative value at the negative bias at the metal. So if band moves upwards, Fermi level moves away from the conduction band, hence depletion of electrons, making it a formation of a depletion region. So you have a thin sheet of minus negative charges and a large region of depletion region of positive charges. Then at inversion you have in inversion you still have your depletion charges, as well as at the interface there's a accumulation of electrons, negative electron charges. So you have a in the metal region you have a thin sheet of negative charges, and in the so this is inversion in a PMOS device. So at the interface your accumulation is of holes for inversion. So you have a depletion region for it. due to depletion of electrons, and then thin thin region for uh, your inversion charges. So we have studied this band diagrams and block charge diagrams. So for depletion region in an NMOS, you have, so for a depletion region NMOS, you have plus positive charges in the metal, negative charge depletion region in the semiconductor. When you calculate the electric field, so you get a straight line in the semiconductor region, and that in the oxide the electric field is almost three times due to the difference in the dielectric constant. When you calculate the potential, it's quadratic with the increase in the value, which is equal to your band applied bias. There's a drop in your oxide, which is called Vox, and a drop in your semiconductor, which is phi s. So, so you have two types of devices. One is NMOS. So an NMOS device, so VG is positive in this case. So this is a PMOS device. In a PMOS device, you have N-type semiconductor, and if you have a P-type semiconductor, it is called a NMOS device. So you can remember that if it is a PMOS device, then in depletion and inversion, you apply a positive. So this is an energy band diagram. So in energy band diagram, if you are applying a positive bias, your metal goes your value goes below the Fermi level, and if you apply a negative bias, your value goes above the Fermi level. So in an energy band diagram, if it is above the Fermi level, you have applied a negative bias, and if it is below the Fermi level, you have applied a positive bias. So here you have applied a negative value of Vg. Vg is negative in this case. It is above the Fermi level. So the Fermi level is here. Vg is here. So you have applied a negative. So you have applied a negative value. Vg is negative here, and therefore there is a negative charge accumulation. Charge accumulation here is negative because you applied a negative bias here. Similarly, here you can see you have Vg is below your Fermi level. So in this case, the Vg is positive, and therefore you have a positive charge, positive charge accumulation. And when you integrate it to get your Vg, you get a positive Vg because you have applied a positive Vg. Yes, in PMOS inversion, you apply a negative Vg to get inversion. So if you apply positive Vg in PMOS, you will get accumulation. So you can remember it like that. This value, this P means at which point you will get accumulation. So for NMOS, accumulation is when your Vg is negative. For PMOS, accumulation is when your Vg is positive. So we have studied this just now. Vg equals to minus Q NaW by Cox plus phi s, where Q NaW is your depletion charge Qd, and W we already know is given by 2 epsilon Si Q Na phi s. So you can get Vg equals to minus square root of 2 epsilon Si Q Na phi s by Cox plus phi s. So here Vg and phi s are epsilon Si Q Na Cox, they're all constants. So this equation is completely between Vg and phi s now. And if you plot this, you will get like this. So this is the accumulation region. This is the depletion region till 2 phi f. After that, it's inversion region. So you can see only in the depletion region there's a strong dependence between phi f and Vg. In accumulation and inversion, there's a not there's not that much huge of a difference between phi f and Vg. So threshold is called when surface inversion charge is equal to your bulk doping. So that is when if bulk charge is phi f, your inversion charge becomes minus phi f. At that is called a threshold point, and at that point you have calculated our psi s is equal to 2 phi f. So we know phi f is equal to ei minus ef, which is given by kt by q ln na by ni for p type, and minus kt by q ln nd by ni for n type. So from that you can now calculate your electron concentration at threshold, which is nst. So this is a p type, so inversion charges are electrons. So nst equals to ni exponential minus q phi f by kt. And add an additional voltage in inversion beyond the threshold, it becomes n inversion equal to Na exponential q phi f plus delta V by kT. So you can calculate from here, you can calculate your change in your space charges with respect to your phi s. This is should be psi s. Basically, this is your surface potential and this is your charge density. So when surface potential is zero, we know it's flat band condition. This is the EI condition where your surface potential equal to phi f. That is called our mid-band condition. And at threshold, your surface potential is equal to 2 phi f. So, so negative when your surface potential is negative for then it's accumulation. So you see here so there's an accumulation of holes. In this region, there's a depletion of holes, and beyond. So there's an accumulation of holes, that is your surface surface holes are greater than your Na. Then in depletion region, your surface holes are also less than Na and surface electrons are also less than Na. Then there's a weak inversion region, that is from mid gap to your phi to from phi f to 2 phi f region. That is called weak inversion. That is still a part of your depletion. So at that point, your surface electrons are greater than surface holes, but your surface electrons are still less than Na. So but in strong inversion region, your sur surface electrons are greater than Na. So you can see so if you want to make a give an equation to this line approximately, so for accumulation, you can say that your psi s is equals to exponential minus psi, your qs charge, your qs is equal to exponential minus q phi s by 2 kt. In the depletion region, it is equal to square root of phi s or psi s, and in the inversion region, it is equal to exponential of q psi s by 2 kt. So in the accumulation and inversion region, your charge is exponentially dependent on your on your surface potential, whereas in the depletion region, it is equal to square root of your surface potential. And this is how the charges will look. For accumulation, the high thin sheet of negative charges on the metal side, thin sheet of positive charges on the uh, semiconductor side. For depletion, thin sheet of positive charges on the metal side, and the depletion region negative charges on the semiconductor side. For inversion, there's thin sheet of positive charges on the metal side, large area of depletion region of negative charges on the whole side on the semiconductor side, plus a thin sheet of large charges, negative charges, which are your inversion charges. So if we want to do exact solution, so so we are doing approximation. So we are doing a delta approximation for charges in the accumulation region, but there is actually some width to it, which will be around 10 nanometers in real cases, and your potential will be around minus 6 kt band bending for band bending minus 6 kt by q. There will be like it will look like this. Your charges will look like this. For middle of depletion, that is when if I is your surface potential is equal to your sur- surface potential equal to your phi f, that is 12 kt by q. That time exact according to depletion delta depletion approximation, it should be a rectangle, but in real value there will be a Fermi dependence on this, and hence it will look like this instead of a rectangle. Then for on at 2 phi f, where it is threshold, it will look like this. So there's instead of a delta charge, there will be a width to it, and here instead of a straight line, there's a curve to it, and deep inversion when so you can see your negative charges are now huge. There's a huge negative charges now. So and hence there's a width here, large width here at the start of your inversion charges. You can see the inversion your charges have jumped from -2 to -400, but your band bending has your surface potential has only gone from 22 to 30. So there's a very small change in surface potential, but a huge change in your number of charges. So your maximum depletion. Now we calculate the maximum depletion width. So after the threshold is reached, further change in gate voltage only increases the number of inversion charges. It does not increase your depletion width any further. So depletion width is maximum at the threshold. After that, only the number of inversion charges increase. So your maximum depletion width is when your surface potential is equal to 2 phi f. So that time, we can calculate your so in so when surface potential in the depletion region, you can say that your depletion width is a square root of 2 epsilon si q na into psi s, and after in the inversion region, it is 2 epsilon si q na into 2 phi f, because that is the maximum depletion width. So you can see for an NMOS device in the negative when your band bending is negative, so when your surface potential is negative, you have accumulation. Surface potential from 0 to 2πf is depletion, and after that is inversion. Whereas in a PMOS, it's opposite. So your surface potential is for when surface potential is positive, you have accumulation. From 0 to minus 2πf, it is depletion, and after to further than that, it's inversion. So here the 2πf itself is so here the phi f itself is negative, given as minus kT by q ln nd by ni. So we know Vg is equal to minus qd by cox plus psi s. So at threshold, which is if we calculate the threshold voltage as a Vg when threshold is achieved, that will be Vt equals to minus qd by cox plus 2 pi f. So in an ideal NMOS case, your qd is negative because depletion region, your holes are depleted, hence qd is negative. Your band bending is positive, so net vt will be positive. And whereas in ideal PMOS case, your qd is positive because depletion of electrons. Your surface potential is negative, hence vt will be negative if when you put everything here. For ideal NMOS, vt is positive. Ideal PMOS, vt is negative. So now you have a example problem. So you have to first get the surface potential. So see here your EI and EF are joined. So your surface potential will be equal to phi f, and phi f here we know is 0.3 eV. So my surface potential is equal to 0.3 eV. Applied gate voltage. So you can see the metal is 0.6 eV below phi f, below my Fermi level. So my applied gate voltage will be equal to 0.6 volts. Now to calculate depletion width, we know is square root of 2 epsilon SI q Na phi s. So Na we can calculate from phi f, which is kT by q ln Na by Ni equals to 0.3. So Na comes out to be 10 power 15. That we can put here. So you can then calculate by putting all the values here to get your depletion width. Next example problem. A MOS capacitor is maintained at T equals to 300K with a Tox equals to 0.1 micron and accepted doping of Na equals to 10 power 15. Compute what is the gate oxide capacitance phi f in volts, W when phi f psi s equals to phi f, and electric field at the interface when psi s equals to phi f. So Cox we can calculate by epsilon ox by Tox. You put all the values. It comes around 36 nanofarad per centimeter square. Then phi f you can calculate by as kT by q and then Na by Ni. So which will come out around 0.3 volts. Now W you can calculate by W you can calculate as 2 epsilon Si with q Na phi f. And then electric field you can calculate by q Na by epsilon Si W. So now we will do some practice questions. For a p-type MOS capacitor, increasing the acceptor doping concentration will increase the threshold voltage, decrease the threshold voltage, have no effect on the threshold voltage, reverse the type of inversion layer. You can write your answer in the chat or you can speak your answer. Anyone knows the answer to this? That is correct. For a p-type MOS capacitor, if you increase the acceptor doping concentration, so it will increase your increase. So it will increase the threshold voltage because your so it increases your threshold voltage because your and phi f will change. For a MOS capacitor with an oxide layer thickness of 10 nanometers, maximum depletion layer thickness of 100 nanometers, and the permittivities epsilon s and epsilon ox are assume epsilon s by epsilon ox equals to 3. Ratio of maximum capacitance to the minimum capacitance of this MOS capacitor is 4.3, 1.5, 2, and 10. So when you are in accumulation, you only have your the only capacity you only have your dielectric as your oxide, but when you are in inversion, you have your oxide dielectric plus your depletion layer also acts as a dielectric. So the answer to this will be 4.3. So in the accumulation, your the capacitance will be equal to Cox, which you can calculate by which will be your epsilon ox by 10 nanometers. But in the inversion region, you will have your capacitance as Cox, you will have two you will have two dielectrics. One is your oxide and one is your depletion region. So you have series two dielectrics in series. So the the capacitance for that will be Cox into C depletion divided by Cox plus C depletion. So Cox is again Cox is epsilon ox by Tox T oxide, and C depletion will be epsilon S by T T depletion. So the maximum depletion thickness is 100 nanometer, and so you put that here. So this will be epsilon ox by so Cox will cancel with Cox, so it will become Cox plus C depletion divided by C depletion. So and epsilon S, you can write it as 3 epsilon ox. So if you calculate if you solve all this, it will come out to be 4.3. So Cox, you can write it as epsilon ox by 10. C depletion, you can write it as epsilon S by 100 or 3 epsilon ox by 10. So this will be 3 epsilon ox by 10, and this will be epsilon ox by, so this will be 3 epsilon ox by 100. This will be epsilon ox by 10, which will be 10 which is 10 epsilon ox by 100. So you can write it as 13. So you will see it will become 13 by 3, which comes out to be 4.3. In a MOS capacitor, inversion is achieved when the surface potential equals the applied gate voltage. The surface potential is greater than or equal to twice the Fermi potential. The depletion region is fully depleted. The gate voltage is negative for an N-type substrate. That is true. In MOS cap, the inversion is achieved when the surface potential is greater than or equal to twice the Fermi potential. When that is when psi s is greater than or equal to 2 phi f. four questions, four questions, 4 to 6. The energy band diagram of a MOS cap device is sketched in the figure below. Assume that the electrostatic potential is 0 in the semiconductor bulk, that is large distance from SiO2 interface, and that there is no metal semiconductor work function difference. Take epsilon ox equal to 3.9, Ni equals to 10 per 10 per centimeter cube, Kt equals to 26 millielectron volts, Eg equals to 1.1 eV, and epsilon Si equals to 11.8. So you are given this band diagram, energy band diagram. What is the value of IF? Minus 0.3 volts, 0.294 volts, zero point 0.3 volts, minus 0.42 volts. So answer to this will be 0.3 volts. So phi f is going to say EI bulk minus, so this is not phi f. So this is written wrong. So phi f will be, so so in an energy band diagram, so phi f is given as EF minus EI. So in an energy band diagram, the lower value is considered positive because we are considering from, so we consider the vacuum level to be zero. So we are seeing everything below this. So the value at the lower value is considered positive. So since EF is below EI, so it is 0.3 volts. So phi F will be 0.3 volts. Next is what is the applied gate voltage VG? 0.42 volts, minus 0.6 volts, 0.6 volts, minus 0.96 volts. Again, you made this again the same mistake. So it's a below EF, so it's positive. Yeah. So it's 0.6 volts, so it's below EF. So as I said, if in the energy band diagram, if it's below, then it's positive. So this is 0.6 volts. So it will be 0.6 volts. So we applied voltage will be the difference in the Fermi levels. So here the Fermi level is 0.6 volts. The metal, the Fermi level is 0.6 volts below. So the VG is 0.6 volts. What is a doping density Na in per centimeter cube? 1.02 into 10 power 15 per centimeter cube, 5.89 into 10 power 16 per centimeter cube, 3.45 into 10 power 15 per centimeter cube, 7.33 into 10 power 15 per centimeter cube. So the answer to this will be 1.02 into 10 power 15 per centimeter cube. So we know phi f is equal to kT by q ln Na by Ni. So phi f we know is 0.3, kT by q is 26 milli electron volts. So if we do this, and it's ln not log, so it's ln, so it will be around, so it's ln, so it will be around 2.3 into log Na by Ni. So if you solve this, if you take everything here, so it will be exponent, so it becomes exponential of kT by exponential point 3 by 0.26, 0.026, exponential of point 0.3 divided by 0.026 into 10 power 10. So solve that, you get 1.02 10 power 15 per centimeter cube. What is the significance of the flat band voltage in a MOS capacitor? It represents the voltage required to achieve strong inversion. It is the voltage at which surface potential is zero. It is the voltage at which oxide capacitance is minimized. It corresponds to the threshold voltage. So the answer to this is, it is the voltage at which the surface potential is zero. So the flat band means when there is no band bending, and if there is no band bending, then the surface potential is zero. Given a p-type silicon MOS capacitor with a doping concentration of Na equals to 1 into 10 power 17 per centimeter cube, permittivity of silicon is epsilon Si into equals to 11.7 into 8.85 into 10 power minus 14 farad per centimeter. Calculate the maximum depletion width when the surface potential reaches 2 phi f, where phi f is the Fermi potential. Assume phi f equals to 0.3 volts. 40 nanometers, 200 nanometers, 10 nanometers, 88 nanometers. So answer to this is actually 88 nanometers. So you have to use the formula W max equals to under root of 2 epsilon SI by Q Na into psi s. So we have to calculate when the surface potential 2 phi f. So instead of phi s, you write 2 phi f, which is zero point 0.6. Epsilon SI you are given here. Q is 1.6 into 10 power minus 19. Na also you are given. So when you put all the values and you calculate, you will get 88 nanometers. On question 9 and 10, the charge plot diagram of a semiconductor is shown. So it should be a MOS capacitor instead of semiconductor. The charge block diagram of a MOS capacitor is shown in the figure below. Which is the correct electric field plot corresponding to the given charge diagram? You have four options. So the correct answer for this will be C. So when you start integrating, there's a huge negative charge. So it will result in a negative electric field, and then there's a huge positive charge. So it will start making the electric field come back from negative back to zero. So when C is the answer, and this gap is due to the difference in the dielectric constants. Which is the correct electrostatic potential plot corresponding to given charge diagram? So again, you have four plots. You have to now identify the potential plot. So the correct answer here would be A, because As you start from the right, your so as you start from the right and integrating, you will have so there's a linear. So you have a linear line, a constant line here. So when you integrate it, you will have a linear line here, and there's a linear line. When you integrate it, you will have a quadratic line. And since the applied since there's a negative charge at the metal, so the applied potential is negative. So the built potential difference here should be negative. So hence A is the right answer. So that is all I had for today. If you have any doubts, you can ask, or if you don't have any doubts, you can leave the session. Thank you for attending.